Humor me tonight by looking at the person sitting next to you. Now look at the person on your other side. This time, really look. Look into their eyes. There is a hidden universe behind those eyes. A world of imagination, emotion, and philosophy. Decisions are made in the hidden matter behind those eyes. Decisions that lead to action, most of the time, but sometimes not. Some people, under extremely unfortunate circumstances, find themselves unable to translate their thoughts and decisions into actions. Some even find themselves locked in. We're used to the facial tells, expressions in that unspoken language that reveal the intelligence behind the face of the living person looking out at us. But for people with ALS or some forms of stroke, a mere eye blink can become their only link to the outside world. Another disease, epilepsy, results when the brain's activity spins out of control, causing a seizure. This affects 65 million people around the world, 3 million in the US alone. And sadly, only 70%, a little over 2/3 of these, will be treatable with medication. Because the inner workings of the brain are hidden, seizures can strike these individuals without warning. So they may be barred from operating heavy machinery, driving, even swimming. Basic human freedoms so many of us take for granted. Furthermore, monitoring epilepsy through EEG, like you see here, can be too cumbersome for the daily surveillance that these individuals need to protect them. Have you ever had a nightmare that you could barely move? For some patients, this is a reality. Patients suffering from Parkinson's can have slowed movement, altered posture, and their body can become increasingly rigid. Approximately 1 million people in the US suffer from this, with up to 60,000 new cases being diagnosed each year. 2% of these will affect people under the age of 40. How do we help these people, our family members, our loved ones, our fellow neighbors? What do all these diseases have in common? The brain. We need to know more about the inner workings of the brain. In the 1950s, scientists and clinicians began reporting evidence of electrical stimulation to treat the symptoms of movement disorders and mental conditions. And since the 1990s, a device akin to a metronome or pacemaker for the brain has been used to provide therapeutic stimulation to structures deep within the brain. This type of therapy, referred to as deep brain stimulation, has been approved by the FDA to reduce the symptoms, some of the symptoms of Parkinson's disease and essential tremor. But interestingly, while scientists, clinicians, and engineers have known that deep brain stimulation worked, they've not really known why or how it worked to affect these symptoms in the brain. This is because scientific and technical limitations have hindered our ability to investigate these questions. For instance, animal models of brain diseases can sometimes be very hard to compare to human brain diseases. And most of the work to record from the brains of human patients has only been possible for brief periods in the operating room during surgery or in specialized epilepsy monitoring units in the hospital. Therefore, we need new scientific research tools to explore and more deeply examine how these diseases are affecting the human brain. From Galileo to Galvani, and from Hubble to Hodgkin and Huxley, advances in scientific research tools have advanced exploration, catalyzed discovery, and opened new insights into the physical world around us and into the physiological world within us. For example, the first of the Voyager space probes, launched in 1977, became the first human object to leave the solar system out into interstellar space. The scientific payloads, the sensors, and arrays of instruments you see attached to that craft send data back to Earth through a telemetry antenna. These scientific payloads have provided new insights into the furthest planets in our solar system and will continue to provide data from interstellar space into the next decade. That's a half-century of scientific discovery catalyzed by this one research tool. How can we uncover the hidden universe of the human brain? Much like the complexity of deploying a complex space probe, it takes a complex system of scientific tools, technologies, and materials to gain access to the human brain. For instance, this massive purple machine you see behind me is a complex electrophysiology system initially developed as a scientific payload for the space shuttle to record from the neurons of rats as they navigated in the weightlessness of space. Scientific research tools like this, combined with analytical tools now considered the domain of data science, have enabled scientists to uncover the first neural evidence that animals experience regret, that they replay their activity during sleep, and that they mentally time travel, their brain activity advancing ahead of themselves to locations they're considering going. With high-tech instruments like this, I investigated similar topics, like how animals form maps of an environment in their brain and switch between those maps to solve problems. But as I thought about the applicability of my work and my skills to helping people, I'd often lament that these systems are far too large for a patient to carry around in their everyday lives, and therefore too impractical for clinicians and researchers to study the inner workings of the brain outside the lab or clinic. What if we could safely shrink even a portion of this monstrous purple electrophysiology rig into something that could fit inside a person? What if we had a mobile system that could send us data about how a patient's brain is responding to disease, to therapies, and to their daily activities? Tonight, I'm excited to share with you a research tool that our research and core technology team that I work with invented, which is expanding the realm of possibilities for clinical research. This new system combines chronic deep brain stimulation technology and has a scientific payload of investigational tools to enable novel research into many diseases in the brain. I have to tell you that we're merely the tool builders, and that this new system is not commercially available in the US, but is classified by the FDA for investigational use only, as part of ongoing physician-led research. The key research tools in this system are the ultra-low power sensing circuitry and memory to record and store the voltage recorded from those neurons. And like the deep space Voyager probe, this deep brain probe has a telemetry antenna to send those signals, the brain waves, out to neuroscientists and neurologists who've partnered with us to explore the hidden universe of the human brain. So what are these sensors really recording? These sensors are recording the voltages generated when currents flow through neurons active deep in the brain. Since neurons act like batteries, charging and discharging, the currents from many, many neurons acting together in different rhythms can add up to cause local field potentials, the scientific term for brainwaves recorded from a small area in the brain. The electrical activity can oscillate depending on the properties of the neural networks and their state, meaning the difference between waking and sleeping, moving and relaxing. One rhythm of particular interest in Parkinson's disease research is the beta rhythm, a slow oscillation, relatively slow oscillation between 15 and 30 hertz. Numerous studies have looked at how the persistent strength of this rhythm seems to be related to the symptoms of Parkinson's disease. Like music, rhythms are typically dynamic. For example, you see here a visual tool called a spectrogram to look at the frequency and intensity of different notes or oscillations. This one is showing the intensity in warmer colors of sound oscillations from a piano, climbing up and down in frequency to create a dynamic melody. But if a rhythm becomes too persistent and monotonous, the normal dynamics are lost. This is analogous to what some studies report about the synchrony of beta oscillations deep within the brain of Parkinson's patients and in animals with Parkinson's-like symptoms. Here's just one such example of data recorded at Stanford using our system to measure the brain's neural activity at the same spot that this system also provides therapeutic stimulation to treat the symptoms of Parkinson's disease. The beta oscillation I mentioned earlier can be seen stretching more or less continuously across the screen as an orangish band of activity between 0 and 50 hertz. Here you can see a few stimulation conditions. Notice that the orange band of activity seems to kind of cool off and disappear as the stimulation goes from 2 volts to 3 volts, and then it comes back when the stimulation is turned down to 0 volts. This is a tantalizing glimpse of what might be called an electrical biomarker in the brain, a signal we hope to monitor so that we can see the response of the brain to disease and to treatments. Note that this system's bidirectional. We can stimulate at the same time as we sense from the brain. Our team is also working on a scalable parallel computing data science system to store and explore these signals further. How many of you have ever listened to Pandora? Watched a movie on Netflix? Bought something on Amazon? What do all these have in common? They collect data in order to provide recommendations to their customers. We hope to use the brain data we collect in our data science systems to recommend possible stimulation settings to clinicians based on an individual patient's brain rhythms. Much like how Pandora recommends music by matching the features of the music tracks to your individual preferences. This is a new approach to precision medicine based on the electrical activity in the brain. But we can go beyond this passive approach. We can imagine an interactive system. Imagine a cruise control system for essential tremor and Parkinson's disease, enabled by a stimulator that can adapt to the desire to move, changes in medication, or can actively eliminate unwanted tremor. We're partnering with universities around the world to investigate just such systems. This investigational work is both exciting and difficult, and sometimes disappointing. In the words of one researcher, the first experiment that I witnessed was with a Parkinson's disease patient. And while it was exciting to see all the technical pieces working, the results were less than exciting. There were many periods of rest tremor breakout where the symptoms reemerged. But since that first experiment, he has been able to see the first glimmers of systems that hold real promise for improving the treatment of these movement disorders. Imagine a traction control system for epilepsy, a device that can detect the brain's activity about to spin out of control and stabilize it before a patient can be disabled by a seizure. Imagine a therapy that automatically adjusts to the brain's needs and adapts to the brain's state. My team member working on this research and supporting sites that are doing this worldwide says, today being a scientist working at medical device therapies for epilepsy is very exciting. What's really exciting about this project is seeing prototypes of therapies we have developed being evaluated in patients for the first time. Or imagine a system to help our fellow humans suffering from ALS and locked-in syndrome. A team of researchers at the University Medical Center in Utrecht, the Netherlands, is working with a patient who's locked in to help investigate a way to allow her to communicate through her computer. They're using our investigational system as part of a neuroprosthesis, or brain-computer interface, to allow her to control her computer using her brain rhythms. The lead scientist described his intense pride and excitement to me the moment they trialed the system with a patient. He said, "We all had the feeling that everything we worked on came together in that one moment when the patient tried the system out the first time. It was an exhilarating experience for the team and the patient." He said the entire team felt a very strong sense of satisfaction that their science and dedication ends up helping patients. These tools are currently for investigational use only and will be worth very little if it were not for the patients and independent scientists and researchers who partner with us in conducting brain research. It's the dedication and strength of their patients, extraordinary individuals, that really make these advancements in clinical neuroscience possible. These patients are the true explorers, taking the foundational step of participating in research to advance our understanding of the brain. Because of them, we can envision improvements into how we treat the symptoms of brain diseases in order to alleviate suffering, restore function, and extend a person's quality of life. Imagine the achievements we can make when we can gain insight into the inner workings of the brain. Imagine the suffering we can ameliorate when we can unravel the disorder created by disease. Imagine a world where we can sense the hidden needs of the brain and respond.